should I go?
Let me just briefly introduce you. So, welcome everyone to the One World seminar on mathematics and machine learning. Thank you all for being here. It's my pleasure to welcome Giulio Biroli from École Normale Supérieure, in particular from the Laboratoire de Physique, where Giulio is a full professor of theoretical physics, and from my understanding, also involved with the Ellis program as a fellow there of machine learning. It's really our pleasure to have him here today to talk about diffusion models and topic of memorization with diffusion models. So please take it away, Giulio.
Thank you very much. So I'm happy, to be here to tell you about our work on memorization in diffusion models. So my collaborator are Tony Bonnaire, who actually was a postdoc at ENS, and now he's a CNRS researcher in the south of Paris. Raphael Urfin, he is a PhD at ENS, and Marc Mézard, who is professor now at Bocconi University. All right, so let me start with, let me see. Yeah, with first the quick introduction. I'm sure that many of you know about diffusion models, but let's be on the same page. So the diffusion models, and more generally, score-based model, are state of the art now in generating images, video, and audio, and 3D scenes. So here is an example of an image of a person that does not exist, but is created by diffusion models. You can create songs, you can create video recently. And the interest in diffusion models is both an interest from the point of view of private company. There are many applications like text to image, for example. Here is an example. Now I think it's even an old figure in which I just wrote the prompt an angry bird, and here you can see what you get. It looks like a bird, and it doesn't look happy. So indeed, it's working well in producing exactly the conditional image that you ask. So this is an example of, let's say, an application that you get from application from private company. So it's used, something that is very interesting, especially for me, that I'm a physicist, is that they have more and more application in science. So for weather forecast, they are really becoming comparable to the best predictive algorithm that there were before. They are very interesting to produce to generate configuration of complex systems. So exactly like they can create a configuration of which correspond to the face of people that do not exist. While we know, for example, in physics that there are configuration like the one that we have in turbulence that are extremely complex with, say, long-range interaction at very multi-scale properties. And so it has been shown, for example, in this paper that generative model, when after training, they can reproduce actually all these complex feature that you find in this complex physical phenomena. And then one topic also that is very interesting, again, for science application, is that, in science, one big revolution has been the fact that you can simulate physical system, and in particular, you can sampling. You can do sample of, for example, equilibrium configuration of physical system. The way to do sampling is using, for example, Monte Carlo Markov chain or dynamical or molecular dynamics. But these are some kinds of physical dynamics, and you could think that maybe there is another way actually to sample, which is using techniques which come from generative models. So this is really a new and very exciting research direction, and which has been studied a lot in recent year. So while this is what you can use diffusion and score-based model to do, and actually what I would like to start is just start with the let's say an introduction to the technique and diffusion models. So what they do, they are based on two processes, one forward process and one backward process. So the forward process, you can see it in many ways. So you can see it as noising, or actually, especially if you are a physicist like me, there is a very nice way to see them as a Langevin equation. So what you do is that, let's say for an image, each pixel is running a stochastic differential equation, which is defined here, which is, a Langevin equation. It's called Ornstein-Uhlenbeck process. And so while during the time, what happens is that each pixel evolves using this dynamical equation. And at long time, which are not that long, already at times of order 10, actually goes to the stationary process. Each pixel goes to the stationary process induced by this stochastic dynamic differential equation. And while the stationary process is just a Gaussian, it's just a Gaussian variable. So this means that if each pixel running this equation is transforming the Gaussian variable, what this forward process is doing is transforming a nice picture, like for example of a dog, in white noise. Now it's very similar, actually, again, as a physicist, this is one of the reasons why actually I started to do this, is that this idea, I mean, this Langevin equation and running Langevin equation is known that, well, what happens is that you relax to equilibrium. The classical example in physics is this one, is you put the ink inside a glass of water and then you wait a long time and while the ink diffuse everywhere. And it's, well, it's the very same physical process. And this is really the kinds of physical equation that in nature you have to use in order to explain relaxation to equilibrium. Now, what is, I would say, very remarkable is that what the diffusion models, and in general score-based model, also flow matching, do is that what they are able to do, they are able to reverse this dynamic. So you can think that here you have a physical dynamics from an initial configuration to, let's say, equilibrium at long times. What they do, they just time revert it. So what they're able to do, time reversing this process, is that, well, what you do is that now you can take a new configuration of Gaussian white noise. And then if you are able to revert dynamically the process, then you can go from white noise to a new sample of the original distribution that you don't know actually. Actually, you just knew data from it. And so this is an example. And how you do to go back? Well, actually, to go back, you can just use, again, another stochastic differential equation in another Langevin equation. So the only thing that changed, if you look at it, is that this part of the force field is reverted. So here you get a plus sign, here it was a minus sign. And then the most important thing is that you have a new force field here, which is called the score, which really is able to drive the dynamics back in time. And now, what is in this force field? Well, in theory of stochastic process, we know what it is the grad of the log of the px of t, which is px of t is the probability distribution of x at time t during the forward process. So let me explain a little bit. So it means that when I'm here during the backward process, the force field that I have to use in order to go backward in time, well, what I have to do, I have to put here on the right-hand side of the equation x, and then to get the s, I should go and see what was the probability of x reached at time t along the forward process. I should take the log, I should take the grad, and this gives me the score function, which is the key ingredient of the force field that I have to use in order to go backward in time. And so while this is an explanation in terms of dynamics, you can also see it simply as noising and denoising. So you could think that this is just, I'm noising this process. And so if I learn how to denoise it and how to denoise white noise, well, this is a denoising process. So I would say there are many different lines of research that arrive to these diffusion models as generative models. There is one which comes from physics, so it's the Soldikenstein et al., which in 2015 actually were thinking about what is called in physics out of equilibrium thermodynamics or stochastic thermodynamics and how to use it to do new machine learning generative models. And they came up with this idea. And then there is a parallel line which comes from theoretical computer science. And then really starting from 2010, this model really started to be used, and then they became really state of the art. All right, so, well, this is, let's say, crash course on diffusion models. And so what I would like to tell you is first, before going in memorization, just to tell you something about, so here maybe, yeah, just to tell you something about the generative process itself and some previous paper that we did. So the first thing that we wanted to understand is what happens during this backward dynamics. In particular, well, we go from white noise to images or, songs or videos that have a lot of structure. So we want to understand how you create structure, how structure emerge from white noise. And so what we did is both combination of numerical experiments and simple analytical studies, in particular studying Gaussian mixture. And so what we understood is that during the backward process, the backward dynamics, there are different regimes of the dynamics. And here I have a small movie that I hope it works. You start, so here is an illustration. You start from one Gaussian and you go from two Gaussian during the backward process. So this is the probability distribution that you want to target with the generative models. And here you see, yes, you start from 3 points, and then you have these 3 trajectories that go backward in time. And now, the first thing that we understood using Gaussian mixture, and then we test this on real data, is that, well, of course, at the beginning of the dynamic, the trajectory are just Gaussian. You have just Gaussian white noise. But then at a certain point, actually, there is the first regime in which the most important features actually of the data forms. So imagine, so here I have an example. Imagine that I trained the model on images of, I think it was bear and seashore. So what happens is that there is a first regime in which actually trajectory will choose whether they go at the end producing a seashore or whether they are going to produce a bear. So it's really the major features. And there is a kind of really dynamical phase transition or phase transition in which trajectory forms lumps, and some lumps go in one direction and other lumps go, the other lump go to the other direction. And so this actually you can, in the case of Gaussian mixture, you can really understood in looking at if you look in the direction which separate the Gaussian, what you have is that there you have a first regime in which you have if you think this dynamics as a particle dynamics, you have that the particles are moving in a potential, which is just like this, which correspond to a Gaussian particle that become just Gaussian. But then during time, this potential change becomes a double well. And now this double well is really the thing that separate the trajectory. So the more you go backward in time, the more actually this two well becomes deep and farther apart, which really drive the trajectory toward one class or the other class. So this is, let's say, the first regime during the backward dynamics. Then there is, again, if you look at so here is the trajectory are together, then they start to separate around here, and you see some, they go in this way and other goes this way. Once they have separated, what happens is that you just start to generate all the high frequency part of the image. So you can see it here, for example, once you have decided to give you a seashore, well, then you have a better and better defined seashore, and here you have a better and better defined bear. And then what happens, so all this analysis that we did was using, well, what we would call the empirical score, or if you want, the perfect score. So means that it's the score that you would use, that the system would use if it was infinitely powerful, and if you were really optimizing the empirical loss. So, and if you use this, what happens is that at the very end, what you get memorization. What I mean by this is that, again, if you look at the trajectory, first regime, they separate in lumps, then they create the high frequency, and then at the very end, actually, the force field, this score, this empirical score, well, it corresponds to forces that are really pushing very strongly the trajectory toward the data that you use to train the model. And so, while this is something that, well, we did in the case of diffusion models, and also other people studied, and in particular, Ricardo also studied from a dynamical perspective, in particular for ODE. So it's clear that, and this is one, I think, of the puzzle that makes this problem interesting, that if you do everything as you should do, meaning you minimize as perfectly as you can with the model most powerful that you can take the empirical score, well, what you get is that the system memorizes. So instead of giving you back new data, it gives you back the data that you use to train it. So in a certain sense, well, diffusion model works because they don't work as they are supposed to. It's really, they don't memorize, but they generalize. And so, well, this is just a summary of what I told you, the fact that there are 3 different regimes. First, formation of classes, then high frequency, and then at the very end, memorization if you really use the empirical score. Now, I would like to enter more in detail of in the memorization and give some detail about the empirical score and the puzzle behind memorization. So let me go back to, I mean, what is the empirical score? So what I mean is that when you have to learn the score function, well, in principle, what you start from is the loss, which is defined like this. So here you have your model for the score function. This means a function of many, many parameters, which in general is represented by a deep neural network, can be a U-net or a transformer. And then what you want to minimize to find the parameters is the mean square loss between the model and, well, the grad of log pt of x. Now, this is something that you don't have because you just have data. You don't know this function, but you can transform in practice if you just do some integration by parts, and then you replace this average, which is here, by an empirical average. You replace this by, well, this score matching loss, the empirical score matching loss that you have here. So here you have the sum over all data, and here you have, let's say, for the data mu, you have the position at time t minus the position actually at time 0 times exponential minus t divided by 1 minus exponential minus 2t. And if you want, actually, you can rewrite this just like the noise. There's an equivalent expression with the noise divided by, let's say, square root of 1 minus exponential minus 2t. And then you can have variance. This is done at a given time t. You can integrate over all time. You can reschedule time. But I mean, roughly, this is how actually you obtain the parameter which correspond to the score function. You just minimize this empirical loss. Now, the puzzle is, as I was telling you, is that there is a minimum. If you just look in function space, there is a minimum of this loss. And the minimum is just the grad of the log of the empirical probability distribution, which is the probability distribution that you reach during the forward process at time t. And this is just a sum of Gaussian. Why so? I mean, if you think just a little bit, well, if you start from n data, so it means that the initial distribution at time 0 is just a sum of delta peak. And for each one of these delta peak is noised during the forward process. So it just becomes a Gaussian with some width. And this is the exact probability distribution, which corresponds to an initial probability distribution, which is a sum of delta peaks. And now it's normal that if you do, in a certain sense, it's normal that if the model, they only know that the only things that it has at its disposal, it's n data, well, so it doesn't know that the probability distribution, the one that you would like to have, is not this sum of delta peaks. And so if it works well, so it means that if the optimization is done as best as you can, and the model is as powerful as you can, so in principle, it will find an empirical score, which is just this grad log of p empirical. And if you use this empirical score as a force field to go backward, then at the end, you will just generate data, the initial data. Now, something that we studied that it has some interest is that, well, what you have is that this probability distribution is sum of Gaussians with a certain width. So it's true that if the Gaussians start to overlap, actually this probability distribution becomes smooth. And at least on typical data, it becomes equivalent to the true underlying probability distribution that you would have with an infinite number of data. But the problem is that because actually the width of this Gaussian becomes smaller and smaller, the more you are close to time 0, actually, in order to have this overlap, and so to avoid, in order that this probability distribution is a good representation of the original probability distribution, you would need a number of data which scale like the exponential of the dimension, which is another way in which curse of dimensionality appears. So this means that, well, if you want to avoid this memorization problem at all times, or generation time, you should use a number of data which is exponential in the dimension, which is clearly not what is done in practice. So the summary of all this is, the first thing is, if you did everything as you should, most powerful model, best optimization, then except if the number of data that you use is exponential in the dimension, you should always memorize. This is not what is found in practice. So the big question is, well, why? What's happening? Why we are not seeing memorization in practice? And now, well, when I say we don't see, well, you see partially in some cases, but it's not, the problem is not as drastic as I was telling you. So let me tell you what you see in terms of memorization versus generalization in practice. So here is an example that we did by ourselves, but there are many other people that study this transition between memorization and generalization in practice. So here, for example, we train a model, let's say state-of-the-art DDPM, on images of, here I think it was conference room and churches. And now what I have here we train it on 200, on a data set of 200 images. And on this column, what you see are images which are generated, so image that should be new. And on this column is the image which is closest to the image which is generated. So I look in the, let's say in the training set. In the training set, I find the image which is closest to the one that has been generated, closest meaning in the L2 distance. And then I just look at them. And what you discover here is that this image that is generated is actually essentially the same, I mean, it's the same image which is the closest that you find in data set closest to this one. Same thing here, same thing here, same thing here. And all the other ones are the ones which are, let's say, the second closest, the third closest, etc. So in this regime, clearly the system is not working, is memorizing, is not generalizing, is not generating new data. So this is the regime in which you don't want to be. Now, the interesting thing is that if you take exactly the same model, so the same number of parameters, you optimize exactly in the same way, same algorithms, same number of epochs. If you increase the number of the images in the training set, so instead of having 200, now you have 40,000, well, what you see is that now, while the image that you generate is no more actually an image that you find in the training set. So clearly, here the system is starting to generalize instead of memorizing. And so this thing of the fact that increasing the number of data and keeping all the rest fixed, you go from memorization to generalization, something that has been seen by many different people. So here is an example actually previous to our paper, in which you have on CFAR10, some kind of experiments, you find that this is the fraction of image which are memorized as a function of the training set size. So you see that if training set for a given unit, so if the training set is small, while you first memorize, you increase the size of the training set, and then you start to actually generalize. So here you have 0 image which are generated, which are in the training set. Interestingly, what you see is that if you take a bigger model, so a more powerful model, well, this transition happens for a large value of the training set size. So you have to have a training set size which is larger when the model is more powerful. So clearly, while here you see an effect which is quite different from what has been discussed in supervised learning in terms of double descent, in which people say, okay, take a very big a very big model, and this is not going to hurt generalization. Here, clearly, if you take a very big model, is going to hurt generalization because you're going to memorize more easily. All right, there is one thing which is important to stress here, is that here in this transition that you have between memorization and generalization, it's happening at a value of n, which is much, much less of exponential of c with constant time the dimension. Because, I mean, the dimension here, don't remember, maybe it was 32 by 32, but, well, if exponential of 32 square, it's certainly not a number which is, let's say, between 200 and 40,000. So clearly, there is a transition between memorization and generalization. It happens when you increase n, and as I'm saying here, this crossover, so there is a crossover at a certain value of n, and now this value of n depends on the model that you have used to learn the score, depends on the kind of data, depends on the kind of the training procedure. It's certainly not, but it's certainly smaller than what you would think from the curse of dimensionality. So this means that, yes, there is memorization, but at the same time, real system escape from it in a regime which is much, let's say, of data, of training set size, which is much smaller of what you would think based on curse of dimensionality. So the system escaped the curse of dimensionality. And again, well, the question is why? Why they do that? And interesting is, well, it depends on the regularization, but with some explicit regularization, at least memorization can also even take place. All right, now again, to show you something about memorization versus generalization, I really liked a lot this numerical example that has been done in this work by Kadokal, Good, Simoncelli, and Mala. And really, this is something that I would like to show you. I mean, it gives you another example of memorization versus generalization, but I think it's probably the best way to think about generalization. So now, well, what they did is, well, here, and the n that you have here is the size of the training set. So here they train, let's say, a model, same model, same training procedure, but they train, let's say, a model on this training set S1, and they train another model, but the same type of model, same type of optimization of the training set S2. So in this case, training set just one image. In this case, it's just one image. And then, while this what you have is that you generate then with the model trained on the training set S2, you generate with the model trained on training set S1. Well, if the training set is just one data, what you get is you get the same data here and you get the same data here. So the two models, S1 and S2, generate data which is not new. They're memorizing. And since one has been trained with a set S1 and one has been trained with a set S2, they are memorizing different images. Same thing here for n equal 10 or n equal 100. What you see, you compare the image which is generated by the model 1 with the closest image in S1, you see it's the same. So the system is memorizing. Same here with the system in S2. You do the same with 100, still memorizing. Then you push. And then at the end, when you are, let's say, 100,000, what you see is that now the interesting thing is that the generation, so the backward dynamics, is done starting from the same initial condition and using the same thermal noise for both S1 and S2. And what you see here is that S1, so the model 1 and the model 2, they are generating in this regime the same image, the very same image, which is not in training set S1 and is not in training set S2. What this means is that despite the fact that the two models have been trained on different training set, they've learned really the same force field, at least on typical configuration, and they are actually running the very same trajectory in one case in the other, which is what they are supposed to do if they are really generalizing, if they really learn for the score, they really learn grad of log p. But it's, well, seeing is I think is probably the most is beautiful way of seeing generalization. So again, also in this case, you see, well, there you have this transition between memorization and generalization when you crank up the training set. And then just to conclude, while memorization, so this has been done, let's say, on dataset, which are, let's say, the one that we can do at university. But then, I mean, you can also use state-of-the-art diffusion models like Stable Diffusion, DAL-E, and it has been shown that memorization, or at least partial memorization, can be found also in that case. Now, the problem, so I think the problem of memorization, from my point of view, is both, it's a very nice problem because it's both theoretical and it's both important for theory, but also for application. It's important for theory because it's at the heart of what we mean by generalizing and generative models. And it's clearly important for, I mean, private company because it's crucial for issues of privacy and copyright. And this is actually one reason also why we started to work on this, just discussing with researchers from DeepMind. Now, the question is, okay, why actually diffusion models not memorize in practice? This is the question that we try to answer in our work. And of course, we are not alone. There are many people that try to address these questions. And you could think that there are many different possible explanations. So one possible explanation that has been discussed by several people, listed here and also others, is that what you could think is that, well, if the model is not powerful enough, so as I told you, the score function, so the empirical score that brings you back to the image, it becomes very regular because it's the gradient of the log of a sum of many peaks. So this is something which in principle could be very difficult to represent if you don't, I mean, if your data set is large and then you don't have enough parameter, the model is not powerful enough, maybe you cannot represent this, so we will try to interpolate. So one possibility is that, well, maybe you have an architectural regularization in the sense that the system cannot represent this function, and so, well, this is why actually you are not memorizing, but you are generalizing. So clearly, well, I think this is clearly an important idea. Now, what I will try to say is that I think there is much more than this, but it's clearly an important point. Then there is another important point is that, well, if you regularize, as is known, as I just told you, the force field becomes very regular, the force field which corresponds to memorization. So if you regularize, then you have to think about the way to regularize, particular while Ricardo has a nice discussion in his paper about the way to regularize. You can also think to the strength of the learning rate as a way to regularize. So if you have some kind of explicit dynamical regularization, maybe then you can avoid or reduce memorization. And I think, again, this clearly can play a role. However, well, what I want to stress is that, well, in practice, for example, well, we know that so the example that I just showed you before, for example, are obtained with model, with UNet, which have convolutional, we have created with convolutional net. So you have some kind of already architectural regularization inside the network. And then also in the training procedure, they have, well, you don't have an infinitely small learning rate, you have a finite learning rate. And despite all this thing, you have seen that if the training set is small enough, the model are able actually to memorize. So, well, our point of view was that there should be actually something else going on. And this is really what I would like to tell you. This just to say that it's not that these other points are not important, but it's more that they are different facets of a more general problem. And now our point is that there is one phenomenon, which is a kind of implicit dynamical regularization due to training dynamics that make the system avoid memorization. Now, let me start with the first, let's say, from the numerical experiments. So what we did here, just to show you, so while we take a data set of images, while we take, well, different number of study training set, very different in size, different unit size, with different optimization, just optimization dynamics, just to see that the results are solid. And I also have to say that these kinds of numerical results have also been found by Favero et al., that they also study text to image and not just image model, and actually bigger images. So what you have here, so let me show you what you have here. So here you have the FID. So the FID is a way to assess the quality of the image which are which are generated. So if the FID is small, it means good images, good quality. And what you have here, so this is tau, is the training time. So what we are doing is that we train until a time tau, the model, then we stop and we use it to generate image. And so, of course, if we stop the training very, very soon, well, we get image which are not good, so the FID is very high. And then, well, if we train it long enough, well, what you see is that the FID goes down. So the different curve that you have here, so maybe, is there a questions or no?
Sorry to interrupt. There is a question from Remy. What exactly is tau here? The number of epochs or the number of iterations of the optimizer?
Is the number of iteration of the optimizer.
Okay, thank you.
So so the different lines that you have here corresponds to the different training set size. So what you have here is that, well, if you change the training set size, so it's so for example, the yellow, well, you have here the number n, so it's increasing. What you see is that this part here doesn't change much. So it means that, of course, well, when tau increase, the quality increase, but more or less independently on the training set size, if the training set is big enough. After a certain time tau, you get image which have generated, which are good quality. Now, something else that you can look at is, well, once you get the image, you want that the image looks good, but you also want to see whether or not they are in the training set, so whether or not the system is memorizing. And then what you see, this is here, this is on this side, is the fraction of memorization. So what you see is that so for example, when n is 112, so here at this training time, you start, if you push the training time after 10 to the 5, well, you start to have memorization. And now the interesting thing is that now what happens if you take the training set larger? Well, you obtain more or less the same curve for the quality of the image, but you push further the time at which you start to memorize. And now I don't know why actually here there is this thing. So let me check. Okay, don't know why. Whoops. Okay. So what you have here is that a collapse of these different curves when you rescale times divided the training time divided by the training set size. So what we did here, we see that these curves actually collapse together if I measure time in terms of the size of the training set. So this means that actually this time that I have here, they are becoming larger and larger when I increase the training set size. And how they becomes larger actually linearly in the training set size. And here is you get similar result, but now instead of looking at the FID and the memorization fraction, we look at the loss, we look at the train and test loss, and you see that the train and the test are exactly the same. So this will be the train and these are the test, and they're exactly the same. So zero generalization error until a certain time at which they becomes different. And you see that this time is pushed on larger and larger tau if we increase the training set size. And again, you can collapse all these, all these times at which the generalization errors start to increase depends on the training set size and depends linearly on the training set size, as you can see from the inset. So, well, and this again is something that we found, but then also was found by the group of Mathieu VR, and then later confirmed by other groups. So what we find is that the time to reach memorization, so in all these cases, if you push training long enough, the system will memorize, but you have to push really long. And how long you have to push it? Roughly, you have to push it as the time to reach a good generalization, so a good quality of the image, times n, which is the training set size. So the model first learned to generalize, and then much later, well, on a time which is proportional to the training set size, start to memorize. So this is the numerics. So we also had studied numerically, analytically, this problem. So we study in the case of random feature model of the score. So random feature is a simple model in which what you do is that you take, let's say, a multi-layer perceptron in which you actually freeze these weights and you just optimize these weights. So this means that the score is written in this way, where the only parameter that you optimize are these A, so these ones, and these ones are taken at random and they're frozen. So it's a simple model that you can study analytically. And so what we did is that we take for data, we take Gaussian data with a certain covariance. We are in the high dimensional limit in which the number of data scales like the dimension, which in both scale to infinity, and the number of parameter p, so the number of nodes that you have here in the hidden layer, also scale with d. And these are two parameters, psi c and psi n, which tells you how much parameter you have compared to the dimension, how much data you have compared to the dimension. Now, well, the way to, well, again, so you can look at the empirical loss in this case. If you just write it down, the nice thing is here is that you see the score is linear in the parameter. And since the loss is just a mean square loss, so this means that the loss is quadratic in the parameter. So at the end, if you study gradient flow as an optimization dynamic, we have a dynamic which is complicated because A is a big matrix, but it's simple because it's linear. So at the end, if the loss is quadratic, when we do gradient flow or gradient descent, we have an equation like A dot minus some, let's say, matrix, which multiply A times some source field. At the end, if we want to understand what happens with the dynamics, we just have to study this matrix U and this matrix V. If you look at the matrix U, since U is multiplying A, so actually the eigenvalues of U are the ones that are controlling the dynamics. So before actually telling you the results, let me just show you that if you just do a numerical simulation for the random features model that I just described you, and if you look at the loss, here, training and test, you find something which is very similar to what I showed you before on real system. These different curves correspond to different sides of the training set. And you see that again, they start to depart, the generalization error start to increase at different times, and these times are linear in n. And this is the distance between the score, which is learn, and the true score, that in this case we know because we are just using Gaussian data. And you see that this distance goes down and goes practically to zero. And then, well, depending on the size of the training set, it can become bigger again, because then you go toward the empirical loss. But this happens later and later, the larger is the training set size. And now, if you want to understand the dynamics, what this is telling you is that indeed you start first you generalize, and then you start to memorize. And since the dynamics, if you want to understand the dynamics, here the dynamics is just governed by these random matrices, and in particularly the relaxation time of the dynamics are just related to the inverse of the eigenvalues of this matrix U plus lambda times the identity. Lambda is the regularization that we put very, very small. And so at the end, the problem boils down to a problem in random matrix theory that we studied. And when you look at the eigenvalues, well, you find that the eigenvalues divide in two bulks. So there is one bulk of eigenvalue which are of order 1, which correspond to relaxation time of order 1. And then there is a very small, actually, bulk of eigenvalues, which if I zoom is here. And these eigenvalues are of order 1 over n. And these eigenvalues are the relaxation times which scale like n, which correspond to memorization. So here you can really work out completely analytically the dynamics. So the large eigenvalues correspond really to a first evolution of the dynamics, at which we have L tests which are of the same order of L loss, and we have zero generalization error. And then actually very small eigenvalues correspond to the second regime of the dynamics, sorry, the ones that I was showing here, or I was showing here, at which you go towards memorization. So we find exactly what we have found in the realistic case. We also find this architectural organization that I was discussing, in the sense that this regime in which the memorization time is proportional to n times the generalization time goes on until actually if you have an overparameterized system in which P is very large, the number of parameters is very large, so you increase n. But when n becomes, in this case, equal to n star, where n star is proportional to the number of parameters, then actually you don't have memorization anymore. And the reason is that here you have so much data that given the number of parameters, the system is not able actually to memorize anymore. And this is something actually was studied before by Macris et al. So let me actually conclude with two illustrations. So here I have a phase diagram in which it's an illustration of the phase diagram, but that actually we found both with numerical experiments and real data, and in the case of random feature model. So here you have the number of data, and here you have the number of parameters. So what happens is that, well, if let's say that I'm here, a certain number of parameters, if I have, so number of data, which is not very large, so the system is memorizing. Now, when I increase the number of data, one start to be in a regime in which the memorization time, so that is here, start to be quite distant from the generalization time. So this gap is opening. And now in all this regime, actually, they have this gap which is opening, and it's opening more and more, more and more, more and more. So it means that actually the system, if I stop the dynamics, it's not even early stopping, because this memorization time is very pushed very far. Actually, in order to see it, you really have to train like crazy. So in all this regime here, the system is implicitly regularized by the dynamics. So it's just that when you train, you have a very extremely slow dynamics in which the train score is very close to the generalization score. And then only if you push very, very, very far, you will go to the memorization. So in all this regime, actually, system can avoid memorization thanks to the training dynamics. And then, well, for this number of parameters, if you, at a certain point, if you really push the number of data very, very high, then at a certain point, indeed, the system enter in the regime of architectural regularization. So the system is the model is not able actually to represent the empirical score because this is, I mean, it's too many, it's a too irregular function. And so in this case, the system is actually it's not memorizing because of this. And here is an example actually of, for example, just to make you understand what happens during the dynamics in a one-dimensional case. So here what you have is in gray, you have the empirical score, as I told you, a very regular function because it's the grad of the log of a sum of peaks. Now the yellow is the evolution of the score during the training dynamics. And now the dashed black one is the one which corresponds to the true underlying generalization score, which is what we would get if you take an infinite number of samples. So this is just a case in which we know what it is. So what you see is that at the beginning of the training dynamics, you start to something which is not equal to the empirical score, is not equal to the true score. But then, well, for a long time, so on all this regime, actually the system settled, so the train score settled down to a function which is very close to the generalization score. And only after a very long time, actually, what you have is that, well, the system will have to move the parameter which model the neural network will have to move in such a way that the train score will be able to represent the empirical score. So it can do it, but it takes a long time. So the thing which is, I think, very interesting, which is behind this implicit regularization by the dynamics, is that it's really the way in which we parameterize the function, the score function, through the neural network that induce this phenomenon. So it's just because the dynamics is not, the training dynamics is not in function space, but it's in parameter space, that, I mean, in the parameter space, well, probably to create this very regular function is possible, but takes an extremely long time. And so the system first actually represents something which is smooth, and then at very long time actually represent which is very regular, which is something that was discussed a bit before in the case of supervised learning and was called the spectral bias. All right, so well, let me conclude. So what I wanted to show you is a mechanism for avoidance of memorization, and is related to the fact that very expressive AI models, they really first to generalize and then much later learns to memorize. And well, there are several follows up actually on which we are working and thinking about is doing well similar things in the case of text generation. And then also here we consider a very strict definition of memorization, which means, well, you have exactly the same data. But of course, in practice, you can think about partial memorization. And this, I think, is interesting in practice, interesting in theory, but it's also difficult to define. And with this, I thank you for your attention.
Thank you very much, Giulio. This is fantastic talk. I really appreciate it. We have some time for questions from the audience. Feel free to either unmute or to put it in the chat. Maybe we can start with Remy, who has his hand raised.
Yes, thanks a lot for your talk. It's very interesting. I have many questions, but maybe one of them is, do you have a good metrics of memorization? Like in the beginning of your talk, you said that if you learn the score perfectly, you will converge to the sum of directs, and so you will memorize. And we can compute this sum of directs term. And so one idea for a matrix of memorization is to compute the distance between this ground truth, which is the sum of direct, and the score function. I mean, for instance, the UNet or the transformer and the architecture. And if you compute this distance, you can have some kind of metric. But do you have a good idea of a metric of this?
So I mean, maybe there are different answers. Depends whether you want to do it in theory or in practice. So in theory, you could look at distances between the probability which is generated by the models and the probability which corresponds to the sum of delta peaks, for example, or the probability would be the true underlying probability, and see whether the system is closer to one or the other. In practice, something that you can do, for example, you could see, I mean, besides this, just, I mean, looking at images, but you could see, for example, whether once you generate a point, you look at the histogram or the statistics of the distance with point in the training set, and you can really see whether there is one which is much, much closer than the other ones with respect to what you would have if this point was, let's say, a typical point at random. So this is what actually is done in practice by many people.
Okay, so like nearest neighbor distance, something like this.
Yes, the statistics of it. Yeah.
Okay,
It
thank
may be
you.
in a feature space, but maybe is what you had in mind as well.
Yeah, you could do it, yeah, in feature space or in pixel space. Yeah.
Other questions? Ma-
Yes, please.
Oh, go ahead,
Yeah, thank you.
Jean-François.
Yeah, thank you.
Hello.
Thank you for this nice talk. I would like to know why you say it is not early stopping.
So
I missed something here.
yeah, no, I think you could call it early stopping, but the fact of early stopping is that, I mean, it's stopping. Of course, you stop the dynamics. What I wanted to stress is that it's a bit different in early stopping. When you do supervised learning in general, you see that, well, you see that you have a training which goes down, you have the test which
Okay.
goes up, and you fix at the minimum.
Yeah.
Here, actually, to see that the system is overfitting, you have to push the training like crazy. So sometimes, I mean, it's you stop it, but it's not because you're thinking that I should stop.
Yes, yes.
Avoid it just it was just this, but otherwise,
Okay. Okay, thank you. I have the difference between one early stopping and the other one. Thank you.
Maybe I can also ask a quick question while other people are asking questions. So, I did have one more technical question, then maybe a broader one. On your analysis, Giulio, of the with the random feature model. So you did mention that you had this regularizer on the weights that was small. But I was wondering if you could comment on if this is motivated by some type of like implicit regularization that's also happening during the dynamics. How do you motivate this like Frobenius norm minimization term
No,
that you
actually,
had?
I mean, it's no, you're right. In practice, so I wrote it, but in practice, we put it to zero. But
Okay,
you're right. One can think about, okay, in practice, I mean, can you put some kind of regularization, which is what you did, and indeed, maybe it would be nice to redo what we did with the kinds of regularization that you discussed. So I just put it there because sometimes when people write random features, they always put this kind of
I
regularization, but
see.
put it to zero actually.
I see. I see. Yeah, it would be interesting maybe if one can connect the lambda directly to some of these scalings with n that you
Yeah.
have.
Ah, I think yes. I think definitely it's something that, I mean, we didn't do it, but you're right. I think it would be one could probably compute the scaling of lambda with n, which is changing between memorization and generalization. Yeah, definitely.
That's good. Thank you.
Thank you.
There's one other question. Oh no, just thank you in the chat.
Can
Other
I ask
questions?
one
Yes, absolutely.
Thank you. Um, so in the second theoretical part, if I understand well, you put a model for the score, a simple model to analyze it analytically. And I relate this to classical results um, for optimization, like comparison between gradient descent and stochastic gradient descent for like MLPs. When you have some theoretical results like uh, the minimum of the minimizer of the loss, it's not the same for GD versus SGD. It's like for SGD it's more parsimonious, things like this. Do you relate this to this kind of analysis, like because you said the word implicit regularization, is it the same kind of things, or am I not understanding well?
No, I would say which is more, I mean, it's how can I say? I mean, the idea, I mean, from the general idea, yes. So it means that is the way in which is the dynamics that actually save the day, but it's slightly different in the sense that here it's not about the fact whether you use gradient descent, gradient flow, or SGD. It's more about the fact that because you do that, so you do the dynamics on the parameter and not on the function. So it's really the way in which you write the function in terms of neural network that makes that the gradient descent is on the parameter, is not on the function, which create this effect. And this effect, you have it whether you use SGD or GD or, I mean, it's other, so it's always there. But it's really the fact that the dynamics is on the parameter, which makes this effect emerge. Whereas if you did gradient descent in, let's say, in the function space, then it would be a different dynamics. I mean, the landscape where you do gradient descent is the same, but the trajectory would be different. So in this sense, it was an implicit regularization by the dynamics. It's the dynamics on the parameter, which is also due to the way in which in the way in which it's the kind of model that one use, which are this deep neural network.
Thanks a lot.
Maybe,
Thank you.
Maybe just a follow-up question on Remy's, if it's okay. Do you have any thoughts on using some maybe the random feature model to design some type of preconditioner to build like a natural gradient descent that's actually more like a gradient descent on the function space?
No, I think it's a good idea, but no, we didn't.
Okay. Okay.
Thank you.
I'm wondering, there might be maybe ways to do some type of preconditioning that might get closer, at least to
Yeah.
dynamics on the functions.
Yeah.
But happy to chat afterwards.
Yep. Okay.
Fantastic. If there's no more questions, I think we can wrap it up here. I want to thank you again very much, Giulio, for the fantastic talk. I really enjoyed it, and I want thank you on behalf of all of the folks here as well.
Thank you. Thank you very much. Bye-bye.